we have the final speaker for this session. So it is Professor Ravi Kumar, and he will present on information security and optical approach. And his biography will be now read by Daniel.
Absolutely. This time I'll get it right. So, Professor Ravi Kumar is an assistant professor at the Department of Physics, SRM University AP in India. He received his PhD degree in physics from IIT in Ahmedabad in June 2018. Before joining SRM AP, he was a postdoctoral research fellow at Electro-Optics Laboratory, Ben Gurion University of Negev, Israel. The fellowship was sponsored by Planning and Budgeting Committee, PBC, of the Council for Higher Education Israel. Prior to that, he was a postdoctoral research fellow at SPART Computational Imaging Laboratory, Nanjing University of Science and Technology, China, and National University of Singapore. He has authored and co-authored around 30 international journal articles and have presented several papers in international national conferences. His research interests are in the field of optical information processing, digital holography, computational/optical imaging, quantitative phase imaging, and optical metrology.
Yeah, thank you very much, Daniel. So now let us welcome Ravi Kumar to give his talk.
Yeah, hi. So first of all, good afternoon to everyone, and thank you, Professor Vijay, for inviting me for a talk in the conference. So today I will be briefly introducing the this information security, how to do with the optics, and why we need this actually. And so this is the This is the outline of my talk. First, I will briefly discuss about the information security and the need for optical techniques in this, and then a few optical techniques. I will start with the first, with the double random phase encoding, which was the first optical technique, which was demonstrated by Professor Javedi in University of Connecticut. And then two of my systems, which I have developed in the past few years. And then I will conclude, and few future scope I will discuss. So information security, actually, I think everyone knows the word itself tells us that how to secure any information, and the need, I think everybody knows in the today's world, it is too much digital information is out there, and everybody is using so many unsecure channels. On that, a lot of personal and important information is passing on to different peoples, and the applications to design the encryption systems or any device which can secure your information are obvious. So to secure personal image, email passwords, government records, military records, all those things. But now the question is, why do we need the optics in it? Because traditionally, when we talk about information security, everybody thought about the digital algorithms or the computer scientist or the encrypting information with the all digital techniques. So the answer is in digital techniques. Actually, they have a few limitations when it talks about information processing. The biggest limitation is in digital algorithms. They process information bit by bit, and it takes time. And another problem is, let's say someone designs a very secure algorithm, there would be someone else who will try to break that algorithm, and if he is computationally efficient than the designer, then of course he will break that algorithm. So the optics actually adds an additional layer of security, in which they combine or maybe purely optical steps which are designed to encrypt information in a way that only the designated users can get the original information. So in our day-to-day life also, we are using several already using some hybrid encryption techniques, such as our smartphones. We are having fingerprints and retinal scans, voice recognition systems, all those things. So now this encryption techniques, actually, they can be classified into two. The first one is symmetric encryption. So symmetric encryption means in which the whatever information which is encoded, you define some keys to encrypt that information. It is like a lock and key system. So a particular key will only open a particular lock. So in symmetric systems, these keys are same while encrypting the information and decrypting the information. But in the asymmetric systems, these keys are different, and the decrypting keys, here you can see the decrypting keys, they are generated during the encryption process, and they will only be like available to a particular persons or the designated users. Now, as I mentioned, the advantages of optical encryption is like in this we can process the whole information at once. The parallel processing it provides us. Then second, it is very hard to replicate the optical systems until or unless you are a you are working in the field. So alongside the algorithm design, you also need to have some experience in the laboratory. It provides high space bandwidth products and the possibility to include biometrics and all the physical parameters such as phase, wavelength, frequency, polarization, angular momentum. All these things can be used as a security keys. So that is also an additional advantage. And also using some these holographic techniques, we can secure information and store information also. So that also solves our problem of data storage. So now, over the period of last 2 decades, actually, this after the development of this double random phase encoding in back in '95, various other techniques have been proposed. So first one was this double random phase encoding actually was proposed using a 4F setup. Then later it has been extended to various other transform domains, Fourier, Fresnel, gyrator, and all those things. And but the problem with this double random phase encoding is it's a linear system. So as I mentioned, there are attacks in the digital techniques. There people come up with the attacks for optical techniques also. So then they recently these asymmetric crypto systems have been designed using various mathematical operations which are combined with the optical methods, mathematical decompositions, and then other areas of optics like diffractive imaging, photon counting imaging, interference, and ghost imaging. All these things have been used for encrypting the information. So now this double random phase encoding, you can see here, it is designed based on the 4F setup. So in this, the information is modulated using 2 random phase masks in the spatial domain and the frequency domain. And in the output domain, we get a noise like random noise like structure, which carries the original information or whatever was in the input plane. So mathematically, it is a simple step. You can see using the 2 Fourier transforms, you have to modulate information at the 2 planes, and then you get the ciphertext. So now you can see to decode information, we need the complex conjugate of these 2 masks. These are the random phase masks. So the original information can only be decoded when we have the correct keys, which are these random phase masks. And when one of the key is wrong, you will not able to get the original information. So which shows the sensitivity of these keys and the strength of the system. So now, if I talk about the few attacks which have been designed recently for the optical techniques. So the most common is noise and occlusion. Let's say you have some sensitive information that it is in the encrypted form, and you are not able to decode it. So the attacker, he may just tear it up, or he may add some noise or whatever. He can try to alter that information so that no designated author user will also be able to decode that information. Another one is the brute force attack, in which let's say you have some encoded information and you have a partial knowledge of the crypto system, how it is been encoded. Then you can apply a brute force attack that you will use n number of random keys to decode that information. And third one is these plain text attacks, which are basically designed based on several phase retrieval algorithms, which are well known in the field of optics. And then the specific attacks. So these specific attacks depends on what kind of a crypto system is there. So based on that, several constraints needs to be designed, and several and the iterative algorithms have been used. So now the system which I will be talking about, I have used the spiral phase transform, which actually it's given, mathematically it can be given by these equations, but if you see physically, so it is a phase in which there is a point where the singular point we try to use, and employ it as a security key. So here you can see at this point the phase cannot be defined. It can be 0 or 2 pi. So like this, we can have multiple singular points in a phase, and the number of singular points will be the key for that particular system. And another I have used is the polar decomposition. So this is purely a mathematical operation which is done in digitally actually. So the systems which I am talking, they are the optoelectronic system or optodigital system, you can say. So here you can see the first system in which I have encrypted an color image. So this color image can be initially separated out in RGB features, and then this spiral phase transform is operated on each feature individually. And then in this system actually I'm using random decomposition, which means that the complex wavefront here, it has been divided into two different complex wavefronts, and one is processed, and this one is used as the private key, which makes the system asymmetric. So for decryption, we only need these private keys to decode the original information, and this the information here, it is further randomized using the chaotic maps. So here you can see this is the final encrypted image after combining all the three individual channels. And this is the simple setup to realize the spiral phase transform. We just have to modulate the information in the Fourier domain by displaying this spiral phase on the SLM. And here you can see some results. So this was the input image which we have used for our work, and this is the encrypted image. And now here I see that all these keys which I was talking about, if let's say while decrypting we don't have access to the private keys or these public keys, we are not able to decode the original information. And let's say if we don't know the order of spiral phase transform, the spiral phase function which is used to modulate the information, then also the original information is not decoded. The original information can only be decoded when we have the correct keys, all the correct keys. So here we have also done the key sensitivity analysis. Let's say if an attacker tries and with some random spiral phase function order, the topological charge order. So a small change in the charge order, you can see these two parameters which I'm using, the PSNR and the SSIM, the structural similarity index, they falls very sharply. And also I have checked with the noise and occlusion attack. Let's say if the additional noise has been added to the encrypted image, and some portion of the encrypted image has been teared out. So still the method is resistant to this kind of attacks. Now, the next system is actually for the authentication system. So in authentication, we don't need to retrieve the full information. A small portion of the original information will also be okay, because in that we will be using this nonlinear correlation. So nonlinear correlation will give us a sharp peak if there is any information available. So this is the schematic of that system. So in this until here, so here after this Fresnel propagation, we use this polar decomposition approach. So this polar decomposition actually gives us one rotational matrix and two positive matrices U and V. So these are the private keys, and then the spiral phase transform, and we get the encrypted image, and then we use the photon limited approach here. So here for this complex wavefront, the amplitude, we limit the number of photons here, and then we decrypt with the correct keys, and then we run the nonlinear correlation operator on that. So if the information is there, it will give a sharp peak, otherwise it will just give a random image. So here this original image is being used, and these are the two keys generated after the polar decomposition, and these are the phase and amplitude of the encrypted image, and this is the photon limited amplitude which is used for processing. So now with using this photon limited amplitude, if we run the decryption and do the authentication with all correct keys, you see the decrypted image is still some noisy, but if as far as there is information there, we get the sharp peak. And in all other three cases, when one of the keys is not available or wrong, then we do not get any sharp peak, which shows that there is no information about the original image, which is decoded by the attacker or someone with who is not the designated user. So with this, I will conclude that optical crypto systems actually, they provide us the enhanced security, and they are very hard to replicate, and they are suitable for real-time applications. And in future, actually, there are several other areas of optics like and the physical parameters such as orbital angular momentum, polarization, metasurface. All these things can be explored to design more advanced crypto systems, and also different kind of beams like Bessel beam, Airy beams, vortex beam. All the properties of these things can be used as a security keys, and which can help to simplify these optical setups, and can actually help in designing some prototype which can be used in real-time applications. So yeah, so with this I will stop. So any questions?
Yeah, thank you very much, Professor Ravi, for your interesting talk. So are there any questions from the audience? Okay, so there is a question from Dr. Vinod. So he has asked this following question. Since you are using multi-wavelength, interested to know how you calibrate the SLM for the operation. Is the modulation poor?
Yes, actually, if you are using multi-wavelength, you have to calibrate SLM. That's true. With every wavelength, that is why actually the main problem with these optical crypto systems, all are theoretical works. Very few experimental works have come up, and mostly the experimental works which I have seen are in the meta-surface domain. So using the meta-surfaces, they have shown few systems, or the traditional DRP-based architecture. Other than that, more complex systems, there are only theoretical studies available. So still, I think people are trying to find it hard due to these problems which is mentioned by. Yeah.
Okay, I understand. So, and I have a question. So when you concluded your talk, you said that it is also possible to use, say, deterministic functions like Yari beams and other types of beams for encryption, right? And also you showed the slide before the conclusion slide, or 2 slides before the conclusion. Yeah, so this one, the authentication is. So in this case, I understand when you use random mask, then I think you get a peak. And if there is even a slight variation, then you don't get this peak. But in the case of deterministic functions like Gary beam or Bessel beams or such beams, so when you use, even though like only a 50% match or 25% match, you probably get not a high contrast peak, but some peak with some value, correct? So how it can be, compared to random method, how it can be used?
Okay, so actually that depends on the crypto system design, full design. So let's say if you are getting 25% of the information retrieved back, so that is the whole goal we are trying to do. That with so much less information, or also we are getting some authentication peak. These systems actually can be, I think, already been in use. When you have your smartphone and you give your fingerprints to it, so it actually captures 3 or 4 different places of your finger, so that from any portion of your thumb or your finger, the information passes, it will be knowing that this is the original user. So yeah, but up to what percentage of information it will be giving, and up to what you want to design your system, that okay, at least it needs to have 50%, then only it should give authentication peak. That those things can be put in like a threshold value you can put in the all digital part.
So I see. So you can engineer it. So that's what you're saying.
Yes,
okay.
yes.
As per the requirement. Okay. I understand.
Yes.
Yeah. Thank you very much.